All right, in chapter 16, part 2, we're going to discuss electrophilic addition. This is a great place for us to start because this is essentially a reaction you already know, and we're going to apply it to dienes, to conjugated dienes. So you should be familiar with the reaction of HBr and an alkene and how you get a Markovnikov product. The bromine goes to the more substituted side, and the hydrogen goes to the less substituted side. If we look at the mechanism, and it's shown on the left, but if you're new to a class with me, I have a hard time talking without also writing. So the first step is the proton transfer. And so we're going to be drawing arrows in our mechanisms. And if you want full credit when you draw arrows in lab reports, then you want to be very clear about where the arrow starts, where it stops, if it's a double-headed arrow or a single-headed arrow. This is also important when you're working your sapling problems. I'm going to go ahead and erase that and redraw it so that I can be more complete. When we pick that proton up, the HBr bond breaks and the bromide ion is released. The reason that this is Markovnikov is because it gives us the more substituted position for the carbocation, which is more stable. So we went from having 2 hydrogens on the end to now having a methyl group. The bromide ion can then go into the nucleophilic attack, and we make our product. Now, when we look at a conjugated double bond like butadiene, we get one expected product. We do get HBr adding across a double bond in a Markovnikov fashion, but we also get, and let me draw it down here, we also get this product where it appears that the double bond is shifted and the bromine is on the end. Now we're going to go ahead and we're going to count through our conjugated double bond. And it has nothing to do with naming. It's just to keep track of this reaction. So if we count from one side of the conjugated double bond to the other, 1, 2, 3, 4, this first product is referred to as the 1,2 product, or you might see 1,2 adduct, either way. And this second product is the 1,4 product, or 1,4 adduct. And both of these are possible, and you usually get some of each. So let's look at the mechanism and see if we can understand why. The first step is exactly the same as the electrophilic addition to your single alkene. You are going to get that proton transfer. We're going to break that HBr bond, and we're going to wind up with, and we'll make this vertical. You're still going to wind up with this carbocation, but we're missing a big part of the picture here. One of the reasons why you will always get a carbocation forming on the 2 carbon, if you count out 1, 2, 3, 4, is because it is stabilized by resonance. So I'm going to draw a resonance structure down below. That positive charge is shared between 2 carbons. So once you look at the resonance structures, it becomes a little bit more understandable how you make the 1,2 and the 1,4 product. Right? Either we get bromine, a bromide ion adding to the 2 position, and that'll give us that 1,2 adduct, or a bromide ion could add to the 4 position, and that would give us our 1,4 adduct. We don't always draw the resonance structures when we do mechanisms, but sometimes it's really important so we can see the whole picture. And here's just Klein has also provided the same thing. He's pointing out here, you will not form a primary carbocation because it is less stable, but even if there was another R group here, you would still form on that number 2 carbon, again, because of the resonance stabilization. And here is the mechanism completed, showing both products. Now, something I want to point out, because we're going to go through lots of mechanisms this summer, or this semester, equilibrium arrows. It's not that they aren't important. You'll notice that I use just straightforward arrows in my mechanism. Typically, when I'm working through a mechanism, I'm interested in moving forward. Some mechanistic steps are reversible, some are not. Both steps happen to be reversible in this reaction. It is a little bit important in kinetic and thermodynamic control, which we're going to talk about in a few minutes. But I don't want you to come away thinking it's not important, but I also want you to understand I'm not going to ask you about the equilibrium arrows. And so a lot of times I won't draw them. Now, we're organic chemists, which means, if you haven't noticed at this point, we're control freaks. We want to be able to control how atoms are connected to each other and how those connections are oriented in space. And so part of that is, if I want to make the 1,2 or the 1,4 adduct, I want to know how I can achieve a major product. And it turns out you can achieve this by controlling the temperature. So something that you need to know to predict products correctly in a reaction like this is that the 1,2 adduct is the major product at cold temperatures. It's also called the kinetic product. We're going to explore that in a moment. Right? This is when 1,2 is the major product. You notice you get 71% versus 29%. If you want the 1,4 product, the 1,4 adduct, you are going to heat it up, right? So 40 degrees, it's fairly warm. We'll say hot versus 0 degrees being cold. This is our thermodynamic product. There we go. So if I give you a problem and I include temperature, I expect you to tell me the one major product. So let's talk about why this occurs. Now, anytime you have kinetic versus thermodynamic control, it's helpful to look at the reaction coordinate. The 1,4 adduct is actually lower in energy. It's more stable because oftentimes you wind up with a more substituted double bond. Right here, you have a mono-substituted double bond. Here is a di-substituted. So it is ultimately more stable. However, it has a higher activation energy. So it takes more kinetic energy to get over that hump. So in cold temperatures, more of your molecules are able to get over the blue and not so many over the red. So more molecules can make the 1,2 adduct. And then it's cold, so even though it's a reversible step, it's even less likely that they'll go backwards. So they kind of get stuck here. However, when you heat things up, more molecules have the ability to get over that higher activation energy. And also, even when you make some of your 1,2 adduct, if it's warm enough, they can go backwards. And so eventually the equilibrium will favor the 1,4 adduct. Now, to answer a question, you don't have to draw this. You just need to know 1,2 is cold, 1,4 is hot. So, and this is just explaining that. Another element that adds to this is the proximity effect. When the HBr bond breaks, the bromine is just going to be physically closer to the 2 position right here. And so there is a very slight advantage, especially if it's cold and things aren't moving around as much, that the bromine would attack that 2 position. And And it helps it form faster. Before we move on, I do want to do some practice problems here and talk about asymmetry. Now, in your slides, asymmetry is not addressed, but I absolutely will ask questions you'll see in the practice and in the old homework assignments. So I want to make sure we do a few practice. So let's start off just with a symmetric problem just to see how a question like this might look. So let's start off with, nope. Sorry. Okay, I know. We are going to use this conjugated double bond. If we treat this with HBr and we heat it up, all right, so we're going to do 40 degrees C. It's going to be hot. Then I know that I should get the 1,4 product. If it helps you to go through the mechanism, I suggest doing that. Otherwise, just make sure you practice a lot so that you recognize, if I count off 1, 2, 3, 4, my hydrogen adds at 1, or my new hydrogen adds at 1, my bromine adds at 4, and I've got a double bond between 2 and 3. One of the more common mistakes is that people forget to shift that double bond. All right, so this is a good basic example. Now, what about if we have asymmetry? Oh, sorry, my brain just totally froze. Okay, we're going to deal with an asymmetric problem next. So here's where I was going earlier. This is an asymmetric diene. Still conjugated. It's still going to give 1, 2, and 1,4 products, but depending on where you start numbering 1 through 4, is going to give you 2 different products. So something like this, if I don't give you any temperature control and I just ask you for all possible products, there are 4 different products. So first, I'm going to go ahead and number top down. The kinetic product would be 1, 2. And then the thermodynamic product would be 1, 4. But what about if I numbered it the other way, 1, 2, 3, 4? Well, the 1, 2 product would put the bromine here. And the 1, 4 product would shift the double bond into that same position, but the bromine would now be up top. It's definitely worthwhile to practice a few of these. Make sure that you don't lose carbon, that you are counting correctly, that you don't just put extra double bonds willy-nilly over on this side of the ring. Those are CH2s. Don't touch them. I definitely will provide some extra practice for you in the extra practice folder. And as we move forward, we will continue to practice problems. Now, I'm only going to touch on this because I do not get into polymers in this class, but this type of reaction is useful in some polymerizations. I will not test you over that, so you can just skip that.